Hello everybody, my name is Morteza Wahid Ghavidel and I'm here to present our work titled Combining Urban Building Energy Management and Expansion Planning of Renewable Energy Systems. These works have been done by my colleagues in Lab for Information and Decision Systems and our colleagues at MIT Sustainable Design Lab from MIT. As an introduction, you know that most of the currently employed early design tools ignore the existing surrounding grids or assume that it will be able to respond to the added energy demand without much trouble. It is also assumed that the grid can meet the required demands of the building. On the other side, the expansion of the renewable energy resources is also known as a solution for decarbonizing the energy systems. So, in the urban areas, renewable energy resources can reach several goals, including the developing sustainable low-carbon neighborhoods and maintaining the reliability of electricity supply for the end users. You can see the changes in the currently electricity grid. In the conventional electricity grid, the energy flow or electricity flow was in a single direction from the generation side to the demand side. But nowadays, the energy flow can be in both sides, from the demand side and also from the generation side. There's also another definition named or called the zero emission neighborhood. In zero emission neighborhood, both the generation and consumption sides are equally important for making robust and efficient energy planning decisions. In the generation size, it is aimed for estimating the renewables potential and identifying the optimal generation portfolio, and in the demand side, it is aimed to estimate the future building loads and their variations over the year, and considering available energy efficiency and demand-side management technologies. Therefore, an interdisciplinary framework is proposed in this work to analyze the electricity requirement of an existing or future urban area to find the optimal mix of generation, storage, and demand solution to meet local energy needs with the low carbon resources. This is the overview of the project that has been done. As I mentioned before, this work is being developed by two teams at MIT. The first section, which is the energy optimization framework, is done in Leeds, and the second section, which is the urban modeling interface, is developed by our colleagues in the MIT Sustainable Design Lab. Our goals are in energy optimization framework section are planning and operation of the local electricity supply, renewable energy storage modeling, and also studying the connection grid, local connection, local grid connection, and also studying the load flexibility and demand response. And our colleagues in the urban modeling interface are working on the urban analysis platform, estimating the building energy requirements and also considering the resident comfort and well-being. The model that we have worked on, it is assumed that the buildings can participate in our model through the demand side management, and it is assumed that our neighborhood is connected to the grid and is also equipped with the storage, which is the lithium-ion batteries, and also renewable energy resources such as the rooftop PV panels and small-scale winds. We have some inputs like the hourly demand requirements, which are called RC models, which being provided by our colleagues from the MIT Sustainable Design Lab, and also hourly solar and wind capacity factors. There are other inputs like technology costs and fuel prices, and local energy market prices and emissions. We want to do an optimization of the generation capacity and hourly dispatch to reach to the hourly load dispatch and the building temperature, optimal cycling of storage units, total system costs, the energy costs for the consumers, amounts of the renewable share, and also impacts of the emissions policies. Our mathematical problem formulation is designed for as a distributed generation planning model, which is a mixed integer linear programming with objective of minimizing the investment and operation costs of the renewables and energy storage units, as well as with the purchasing from the grid. Our constraints are the energy balance, generation units, operational constraints, building thermal modeling for demand-side management purposes, battery constraints, including the degradation costs, and also CO2 emissions constraints. As I mentioned before, we have considered our building as an RC model. In this RC model, each building or each room is considered with a specific amounts of resistance and the capacitance. And with this resistance and capacitance, we can reach to a, and also having information about the ambient temperature, we can reach to the relation between the room temperature and the ambient temperature, as you can see here. And also we are assuming that the buildings are represented as a shoeboxes or Lego pieces with the RC model. So each building consists of specific RC models. We just consider it as a shoebox with a RC model. So with this information, we can do our analysis and optimization. Our case study is considered to be a neighborhood in Chicago, Illinois, which we have the retail and the community residential buildings and also offices. We have considered that number of the occupants are around 15,000 people. The inputs for our case study, we are considering 16 different Legos with different thermal properties, and also for each Lego, the time series of hot water equipment and lighting power and ambient temperature and power gains are also being given. There are a series of assumptions for the grid, renewables, and storage, such as the hourly local market prices, hourly carbon intensity, hourly PV and wind local capacity factors. And as a scenarios, we are considering several scenarios. In the first scenario, we're considering it that our neighborhood is working with only grid or business as usual. So it is not connected to the renewable energy sources, neither the battery. In the second scenario, grid plus battery is considered. The next one, only grid and the renewables are being studied, and on the other one, the grid with the both renewables and battery are being studied. In the next one, we have considered that the prices from the grids are the fixed tariffs, so there is no variation over the day for the different hours with the renewables and battery. And the last case, we are considering that if we have a 25, 50, 75, or 100% of emission costs, how much emission cuts, how much energy or installed capacity we need to have. As a result, in this figure, you can see the installed capacity in different scenarios. In the first scenario, is business as usual, so we consider that there is no battery or the renewables. But by considering battery, you can see that the percentage of the penetration from the grid will be covered by the battery. But in the if we consider our model with the grid with only renewable energy resources, you will see that we will require a high investment in the amounts of the PV. This is because of uncertainty nature of the production from the PV. Because of the high uncertainty level, we require a high installed capacity to cover to meet our demand that we are required. In this result also we have the CO2 emissions for different scenarios. You can see that the business as usual carbon intensity the business as usual carbon intensity is around 474 gram per kilowatt hour. If we consider the battery grid with only battery, you can see that we have a slightly higher emissions due to the cycling efficiency. But by having the grid with only renewable energy resources, we will have a 31% lower carbon intensity compared to the business as usual. And we will have even lower carbon intensity if we combine and have both renewables and battery storage to our grid. But in the last one, due to the lower energy prices with the fixed tariff from the grid, our emissions will be increased. And also there are results regarding the carbon emissions reductions. As you can see in the top plot, there's an installed capacity in different emission scenarios. You can see the dominant role of the PV that in all of the scenarios, and the other noticeable point is that if we want to have 100% emission cost or zero emission planning, we need to have a 6 times larger installed capacity with our if you comparing to 25% emission costs. And in the bottom figure you can see that the energy costs in different scenario, which you can see that the difference of the energy costs from 25% to the 75% are not they do not have a very large difference, but we will have a substantially higher cost when we jump to the 100% emissions cut. So and this is because of the 23% of the load. This is because of that the 20% of the total cost cut from the load curtailment due to the demand response programs. As a conclusion, we have developed several ideas for how to best connect energy and power system modeling. We have implemented RC model concept as a building grid link and reaching to a minimum energy cost by application of energy storage and renewable energy resources. And also the significant role of the renewable energy resources in the reduction of the CO2 emissions are being shown. Thank you very much for your attention.